Earth looks simple from space. But divided into two hemispheres, and a completely different planet begins to appear.
Humans have traveled 300 to 84,000 kilometers to the Moon. Yet the deepest vertical hole ever drilled on Earth reaches only 12.262 kilometers. On a full cross-section of the planet, that record is almost invisible, less than 0.2% of the distance to the center. The core does not begin near that depth. It starts roughly 2,900 kilometers below the surface. So, why have we never come remotely close to reaching it? The first problem is scale. Deep drilling is not a giant open pit. It is a narrow borehole built for tools and pipe. Steel casing supports the walls, but every new section must fit inside the one above it. As the hole deepens, it becomes narrower, leaving less room for stronger tools, sensors, cooling, and repairs. At the Kola Super Deep borehole, Soviet engineers spent decades drilling through ancient crystalline rock. They reached 12,262 meters, but temperatures near the bottom exceeded 180 degrees Celsius, far hotter than expected. Under that heat and stress, rock is not perfectly rigid. It can fracture, deform, and slowly squeeze the borehole. The drill bit wears against abrasive rock. Replacing it means pulling kilometers of pipe to the surface and lowering everything again. Pressure distorts casing and can trap equipment. Drilling fluid must cool the bit, control pressure, and lift fragments. If it escapes into fractures, circulation can fail. One damaged section can strand equipment far below the surface. Even crossing the crust is extremely difficult. Beneath continents, the crust mantle boundary may lie tens of kilometers down, far below the Kola record. Oceanic crust is thinner, so scientists have tried to reach the mantle from drilling ships. But that creates a different problem. A ship must hold position while kilometers of pipe hang through deep water. Wind, waves, and currents push the vessel away. Dynamic positioning can correct the ship, but the drill string still bends, vibrates, and accumulates fatigue. No controlled borehole has yet completed the journey through intact crust into the mantle. And reaching the mantle would still be only the beginning. The mantle extends for almost 2,900 kilometers. It is not a global ocean of magma. Most mantle rock is solid, but over geological time it can flow slowly under immense heat and pressure. Near the core mantle boundary, pressure reaches about 136 gigapascals, more than 1 million times ordinary atmospheric pressure. Temperatures rise to several thousand degrees. Conventional drill bits, motors, sensors, and fluids could not survive. Heat would destroy electronics, weaken materials, and make the borehole unstable long before a machine approached the core. The opening itself would fight the operation. Surrounding rock would try to close it. Steel casing could distort or fail, while cooling fluid would heat rapidly and struggle to return. Then comes the outer core, a liquid iron-rich layer roughly 2,200 kilometers thick. There is no solid wall to keep drilling through. A probe would have to survive extreme heat, crushing pressure, chemical attack, and a moving, electrically conducting liquid. Every extra kilometer adds temperature, pressure, time, cost, and new ways for the mission to fail. Yet we still know the core exists because earthquakes send natural test signals through the planet. P waves can pass through solids and liquids, but they change speed and direction at boundaries. S waves travel through solid rock, but they do not pass through the liquid outer core. Their disappearance, together with the bending of P waves, creates global shadow zones that reveal a liquid layer deep inside Earth. Seismologists compare earthquake arrival times recorded around the world. A wave that arrives early suggests faster material. A delayed or missing wave points to a boundary or liquid region. By combining thousands of earthquakes, scientists build three-dimensional models of structures no camera can directly see. Gravity, Earth's moment of inertia, its magnetic field and high-pressure laboratory experiments provide independent evidence. In diamond anvil cells, tiny samples are squeezed and laser heated toward deep Earth conditions without sending a machine underground. So, our picture of the core is indirect, but it is not a guess. Different measurements converge on the same internal structure. Reaching it physically would require drilling, cooling, and materials technologies far beyond today's limits. The realistic next milestone is not the core, it is the mantle. Earth's center remains untouched, not because it is magical or unknowable, but because the planet becomes an extreme engineering environment almost immediately beneath our feet.